Hello and welcome back to our GPU optimization of Advanced Encryption Standard course. So this is the third lecture. In the first two, we talk about block ciphers, and as an example, we have seen Advanced Encryption Standard. Now we are going to talk about modes of operation because we should determine how we can encrypt data that is larger than a single block. So that is one of the main considerations because when we defined the block cipher, we said that it divides the plaintext into B-bit blocks and then operates on these B-bits, provide output, and then somehow turn it into ciphertext. So in this respect, the first thing that comes to mind is this following solution. So if I have large data, like n plus 1 blocks, I can divide it into n plus 1 blocks as in this picture. Encrypt every block independently using the same secret key, right? So this way I obtain encrypted output blocks, and if I concatenate them, then obtain the ciphertext. So for the decrypting part, the person who receives the ciphertext decrypts all of these blocks independently and obtain the plaintext block. So encryption and decryption works as long as you have the secret key K. So this looks like a nice solution, and it has a lot of properties like it is parallelizable and so on. For instance, you can encrypt the plaintext block P0, P1, and P2 simultaneously if you have, for instance, 3 cores. But the main problem here is that this is actually the worst idea. You shouldn't be using this. This approach is called electronic codebook or ECB mode of operation. But here there is a huge problem. Since we are doing the same operation, because a block cipher is a fixed transformation. So if two blocks are identical, for instance, if P1 and P2 are identical, since we are encrypting them with the same secret key, C1 and C2 will be identical too. So this actually leaks an information about the plaintext. So you might think that this might rarely happen because we are dividing the plaintext into 128-bit blocks. So it might be highly unlikely that there will be two identical blocks. But actually the plaintext, regardless of the context, generally have huge redundancy. So a lot of things repeat. So if it is a text, for instance, same words, same letters. For instance, in English, the letter E appears more frequently. So depending on the context, some things appear more frequently. So the plaintext has redundancy. So as an example, let's look at an BMP file and then let's encrypt it. So look at all of these white pixels here. So if I divide this plaintext into blocks, many white pixels, consecutive white pixels, will be the input of our encryption because it will be a plaintext block. So all of these white plaintext will be encrypted to same thing. So if we use AES with 128-bit key, but in the ECB mode, this is the result of the encryption. So this is the original picture. This is the encrypted version, which tells a lot about the plaintext. We can even see the logo. We can even read the name of the university. So this is why even if you have a algorithm that is secure, you should also choose a secure mode of operation, and ECB is not one of them. So one quick solution might be this. This one is called Cipher Block Chaining mode, CBC mode. So here we actually combine these blocks with these arrows. So for instance, you encrypt P0, obtain the first output block C0, but you also XOR it with the next plaintext block P1 and then encrypt it. So in this scenario, if P1 and P2 are identical, after this XOR operation, so most probably they will be different. So after the encryption, they will be different too. So here IV stands for initialization vector. It doesn't provide any security. It is just to, keep the symmetry in the picture. But here, since we connected these parts, now we lost parallelizability because if I want to encrypt P2, I need to perform this XOR operation. So I need to know the value of C1. But in order to know the value of C1, I should encrypt P1 first. But in order to encrypt P1, I need to know what is C0. So this is why I need to encrypt P0 first and so on. So this is a serialized mode of operation, which will not help me in GPU optimization because I want to encrypt each block at the same time with different threads or cores of the GPU. So this is why we need another mode of operation. So there are many modes of operation, and NIST generally in their document has 5, but they are going to update this document, so I'm not going to refer to all of them. But counter mode of operation, CTR in short, is a very nice solution and very suitable for GPU implementation because here things are a little bit different. So we sometimes choose a nonce. Nonce is a random value that is only used once. So when you're, for instance, if you're encrypting something, you can choose a nonce, but in the next encryption, you should choose something else. So this is just to provide randomness in the input. And then you choose a counter. For instance, assume that you choose all 0. So here you encrypt your counter concatenate to the nonce. So instead of encrypting your plain text, you are encrypting actually publicly known value, but the result will not be known by the attackers because they don't have the secret key, so they cannot perform the same operation. And then you XOR the output with your plain text block to obtain the ciphertext block. So this is a little bit different because we don't have PIs at the top. Instead, we are encrypting some values. And as you can see, there are no connection with these parts because here we simply increment the counter by 1 and encrypt it, increment it again and encrypt it and so on. So this way we have parallelization. And we also solve the problem of ECB, which, same blocks are going, same plain text blocks encrypting to same ciphertext blocks. So here, even if P0 and P1 are identical, since the counter values are different, the output values will be different. So the XOR operation will give you something different. So let's go back to our motivation and see what happens if I use the counter mode instead of ECB. So recall that this was our plain text, a BMP file, and we said that if you encrypt it with AES using 128-bit secret key, but in the ECB mode, this is the output. But if you use the counter mode, this will be the ciphertext. So as you can see, there are no patterns, nothing that human eye can detect. So if I go back, original picture, ECB mode of encryption, and counter mode of operation. So this is why you should choose your mode of operation carefully, and also, you shouldn't be using something weak. So this concludes our discussion of modes of operation. So in the next lecture, we will start implementing things. First, we will see how we can implement AES using the C programming language. Then we see how it is done in CUDA. And then in the following lectures, we will also optimize it for CUDA. So thank you for listening.